We're going to be looking at a lot of vocabulary that we'll continue to use throughout the year. And if you're ready for this lesson, you have your vocabulary that you did for homework. You've got some basic definitions in your notes, and you've left some space to add more information because we're going to cover a lot. So I hope you're ready. We're talking about the classification of matter, and we're learning a lot of words that we use when we describe and classify different kinds of matter. We've talked about what matter is. It's anything that's around us. We've talked about how almost everything we can think up is matter, right? Anything we can touch, anything we handle. And the formal definition, it has mass and takes up space. And we know from previous knowledge that matter is made up of atoms. And an atom, which is one of your words, is the smallest unit of an element that has all the properties of that element. It's the smallest piece of that element that exists. It's called an atom. When we talk about matter, we've talked already about the three states of matter when we've described physical properties. We'll talk about what state that substance is in at room temperature, and we also talk about what temperature something melts at or what temperature something boils at. And so we're familiar with the states of matter, but to clarify a little bit deeper, when we talk about the three states of matter, when we talk about something that is a solid always has a definite or fixed shape. A solid has a shape that's not changing. Okay? A liquid does not have a fixed shape. If you pour a liquid from one container to the next, it'll take the shape of that container. And a gas also does not have a fixed shape. It will take the shape of its container. So it'll fill a whole room if there's no other thing to contain it. Volume, again, then for a solid, it has a fixed volume. A liquid will have a fixed volume because if you pour 500 milliliters of water from a container that's shaped in one shape, pour it into another shaped container, you're still going to have the same volume. You'll still have your 500 milliliters of water, but the shape will change. And then a gas does not have a fixed volume. It will spread out to take not only the shape of the room or the shape of a container that it's in, but it'll fill the whole volume of that container. And then when we talk about the particles of a solid are organized and rigid. They have their own little position that they're in, and they don't move much. Particles of a liquid flow. They move past each other. They can slide past each other. And then, of course, particles of a gas are moving in such a way that they do spread out and fill the container. So there's a lot more space in between them. So when we look at the states of matter, we often talk about them with pictures. And those pictures that show the actual particles, the actual pieces of matter, we call those particle models. So this is some particle models to show us a little bit about solid, liquid, and gas. You can see the gas has a lot of space in between. The liquid, they're close together, but they're not highly organized because they're moving and sliding past each other. And then when you look at the solid, they're very close together and in a very rigid pattern. So as we look at all the categories of matter, anything we talk about in the rest of this idea that we're going to cover, this way to categorize matter, we can talk about solids, liquids, and gases in almost any of the different categories. So those are some overriding ways that we look at and notice and observe the matter that we're seeing. So we're going to start here. Again, what is matter? Anything that has mass and takes up space. And here we have a picture of oil being poured into water. And when we look at this, we are, as regular, students who aren't thinking about chemistry, we really don't think that much about it. It's like, okay, there's the oil, there's the water. You can see that there's two substances there. But in this section of our course, we're really going to be starting to think like a chemist. And when a chemist sees this picture, they're thinking about what they see. Yes, you can see the oil. Yes, you can see the water. But they're also thinking about what you can't see with our eyes. And that's what we call the submicroscopic characteristics of matter. Now, this other word, the macroscopic characteristics of matter, just means what we can actually see with our eyes. When we talk about there's oil, there's water, they don't appear to be mixing. The oil has a little bit of a yellow color. The water is clear. Physical properties. They're both liquids. Those are macroscopic properties. That's a macroscopic description of what's there. But a chemist will also think about the fact that both of those substances are made of molecules. And they know things that we don't know yet, right? But they know what a water molecule looks like. And a water molecule is what you see here. There's 3 of them in this drawing. And then that is a molecule of oil. It's a much larger molecule. Every one of those little circles represents an atom that's connected to the rest of the atoms there. And that's called a molecule. It's a big molecule. And here with the water molecule, it has 3 atoms, an oxygen and 2 hydrogens. So it's a relatively small molecule. Okay. So as we go through this, we're going to begin thinking like a chemist. So we're going to think about what we see, and we're going to think about the particles that are there that we don't see. So we're going to change our thinking a little bit. All matter, all of it, can be divided into exactly 2 categories. That's it. It's one or the other. No matter what we're interacting with, it's either a pure substance or it's a mixture. And since we know what a mixture is, talk about that for a minute first. A mixture is just more than one kind of matter mixed together. More than one kind of atom or molecule mixed. Mixture. Pure substance is a little bit trickier because the way chemistry uses the phrase pure substance, the way a chemist talks about a pure substance, is different than the way we hear the word pure used in industry and marketing and advertising. If you go to the grocery store and you pick up a bottle of orange juice to take home, it might say 100% pure orange juice. And when it uses that word pure, it's suggesting that there wasn't anything else other than the orange juice put there. It means clean, healthy for you. No other additives. But a chemist, when they see orange juice, they would not call that pure. It doesn't mean that there's other stuff that's been added to it, but they think about, well, what's it really made of? How many different kinds of atoms and molecules are there? And in orange juice, there's all kinds of different things there. There's naturally water in an orange, and then there's whatever chemical makes the juice orange that comes from the orange. It's all natural. There's the citric acid that gives it the tang. There's sugars naturally in orange juice. There's some pulp and fiber in a lot of orange juice, unless it's been strained out, right? So there's a whole lot of different things in orange juice. So to a chemist, orange juice is not pure because it's a mixture of different things. When a chemist talks about a pure substance, it means that all the tiny pieces in that sample are exactly the same as the others. So either a pure substance is going to have all the exact same atom, which is what that is, or it's going to have all the exact same molecule. And when we see these little circles that represent atoms touching each other, we're talking about a bond there, and those are molecules. So every teeny tiny piece of a pure substance is exactly like all the others. Otherwise, in a chemist's eye, that's a mixture. So when we look at pure substances, either a pure substance is an element or it's a compound. That's it. Either a pure substance is going to be an element or it's going to be a compound. Now, we know that there's the periodic table of elements. We've seen that. We've talked about it in middle school. We've learned a little bit about it over the years. We know there are things like oxygen and carbon and silver and gold and copper, helium and hydrogen. We know some of those elements. Okay? So an element has all the same kind of an atom there. All the atoms in an element are exactly the same as all the others. So one thing we can say is that an element's going to have all this exact same kind of atom, and we can also kind of add to our thoughts. If it's an element, it's on the periodic table. If it's not on the periodic table, it's not an element. Okay? When we see the symbol that's written for an element, like oxygen, okay, calcium, fluorine, chlorine, okay. If it's an element and we're looking at the symbol, it only has one capital letter. This is important. This is a nice, easy way to know. Am I looking at something that is an element, or am I looking at it as a compound? With the macroscopic properties, a lot of times we don't know till we get familiar with these different substances. But if we see something and the symbol for it is AU, it only has one capital letter, that's an element. Okay. If it has two capital letters in this symbolic representation of it, like water, H2O, you've seen the water symbol before, then it has two elements bonded together. Okay. So pure substances are one of two things. Either it's an element or it's a compound. Okay. Another common compound, and we'll see a lot of examples, is table salt. Two capital letters. Okay. So let's talk more about elements and compounds. Here's some examples. Here's copper, which is an element. It has its own box on the periodic table. It has this symbol, Cu, one capital letter. And it exists as a solid. You've seen copper before. We've used it in the lab. And all those atoms of copper are close together. It's a solid. Here, bromine. Bromine has a 2 in its symbol because it exists as a set of two bromine atoms connected together. This is an element because every atom in the sample is exactly like all the others. It just happens to be hanging around in sets of two, bonded together, and we call that diatomic element. Di means two. Okay, diatomic element. And then this bromine is interesting because it goes into the gas phase really easy. So if it's stored in a jar like this, you'll see it's a solid, but then it's kind of up into the air. It's a gas. It has a gaseous nature. It's an interesting element. So this third picture is of a compound, carbon dioxide, which you're familiar with. We exhale carbon dioxide. Plants take in carbon dioxide and give off oxygen, and we take in the oxygen and give off carbon dioxide. Should have learned that in biology, I think, right? So this is frozen carbon dioxide. It's what we call dry ice. And it's a compound, carbon dioxide. When you see the symbol for that, two capital letters, that's how you're going to know. If you see two capital letters, that's a compound. Okay? And now you can see the submicroscopic view. What is what does the part we can't see with our eyes look like? You can see that there's more than one kind of atom there, and they're all bonded together into that carbon dioxide, which in this case is frozen, so it's a solid, right? When we talk about elements, of course, I did say if it's not on the periodic table, it's not an element. It is a substance that cannot be broken down into a simpler substance. Okay? These are the smallest building blocks of all matter. Again, they only contain one kind of atom. And if we want to find a list of them, we have our periodic table. One atom of an element has all the properties of any sample of that element anywhere. So even one atom of copper has that, it's so small we can't see it, but it has that brown color, it's a metal, it has the same luster. The atom, each atom has all the properties of that substance. An atom is the smallest piece of that that will have those properties. Not all elements exist as atoms. The diatomic elements exist as molecules. There are 7 of them. Eventually, you're going to have to know which ones they are. Okay? They're hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. Some people call it the Han family because the first 3 here spell out Han, and if you look at the periodic table, fluorine is over on the right, and right underneath it is chlorine and then bromine and iodine, and they are in a column that we call a group. They're a family. Okay, so the Han family means we've got HON, Han, and fluorine's family there. Just one way to remember it. There's a lot of different memory devices. I brought clay for our new house is one I've learned from another teacher. I brought clay for our new house. Have no fear of ice cold root beer, or I say broccoli sometimes. Have no fear of ice cold broccoli. You can make up your own, but someday you're going to need to know those. So when we talk about any of these substances, these are pure substances. We're talking about elements and compounds. We are interested in categorizing them correctly, but as a chemist, we're also interested in talking about what they are composed of on that submicroscopic level. We want to talk about particles. And so the word we use for these little pieces are particles. And the particles are atoms and molecules. That's the particles we're talking about right now. And so we want to talk about what are they. So copper exists as atoms. Bromine, because it's a diatomic element, exists as molecules. And carbon dioxide also exists as molecules. Here's some more elements. And I lost my formatting when I converted this and missed my R's in the wrong place there. And I don't know where the L went, but there it is. So here are some other examples of common elements. Each of these have their own box on the periodic table. Some elements are metals, some elements aren't. Some elements are gases. Helium, this isn't the plastic that we're talking about. We're talking about the helium in the balloon. Sulfur is an interesting element. It's formed in volcanic areas, and it's got a really strong smell. Compounds that have sulfur in them tend to have odors. So all pure substances are either elements or compounds. Okay, so what is a compound? Well, a compound is a substance that is made of 2 or more atoms of different elements bonded together. 2 or more elements chemically bonded together. Okay, it can be broken down, but it takes a chemical change to break that down, okay? It's not going to break down in a physical change. A chemical change is required to make a compound out of two elements, and a chemical change is required to take those two apart and put them back into elements, two or more. So things we mentioned: water, carbon dioxide, ammonia has a nitrogen and 3 hydrogens. It's a gas. It's a nasty gas that would be very irritating to your bronchial systems. Methane, here's methane, which we call natural gas. That's the stuff we use when we're burning in the Bunsen burners. Okay, different kinds of compounds around us. A molecule is referring to not the category of substances, but the particle. So a molecule is when 2 or more atoms are bonded together with shared electrons. And when we draw a molecule, we're just drawing a representation. We're going to just take a couple of our circles that we use for atoms and draw them touching. So whenever you see drawings and the particles, the atoms are touching, that's always suggesting a molecule. It's 99.9% of the time. And here we have molecules that are elements, the diatomic elements, and we have molecules that are compounds. This is really an important screen because it clears up something that students kind of pick up an incorrect idea in elementary school. If they have a pretty extensive science program, they sometimes think that all elements exist as atoms and all compounds exist as molecules, but that's not true. 7 of the elements, the diatomic elements, exist as molecules, and then the compounds as well. So compounds are formed when 2 elements react together in a chemical reaction. And one way that that happens is when an electron transfers from one to another, but that's a lesson for a different day. But something happens, and so they are chemically bonded together. So we have sodium, which is a shiny metal that's very dangerous. You can't really touch it. It's very, very harmful. It's not like aluminum that we can handle and copper that we can handle. And then chlorine, which is a gas. So we have a solid and a gas, and if they react together, both of those chemicals or elements are pretty dangerous, pretty hazardous to have around. Pure chlorine is very hazardous. But when they react together, the properties change. Remember, we talk about how a chemical change is when a new substance is formed, and so that new substance has different properties. And what we get when sodium and chlorine react is table salt, ordinary table salt, not dangerous at all. 2 very harmful, hazardous elements react together to form something that we use all the time, salt. So again, compounds. Salt is an example. I like this because I like to see the pretty crystals of salt. Sugar is interesting because it's formed a little bit differently than salt is, but it can also form a pretty nice looking crystal if you work with it right. And sugar has a pretty big molecule. Like we've talked about water. Water has a molecule that looks like Mickey Mouse, okay? It always has a small molecule, H2O. And sugar has a big molecule. It's a compound. Baking soda is a compound. Okay? Its formula is Na2CO3. Notice 2 capital letters. If you see 2 or more capital letters, you are looking at a compound. Sodium bicarbonate. Water is a compound. sulfuric acid is an example of a dangerous compound. And this is a picture of a sulfuric acid bottle. And then this is a photograph of the kind of skin damage that sulfuric acid burns can cause. And so if we have to work with certain kinds of chemicals, we have to understand safety procedures and we have to follow them. We don't work with concentrated sulfuric acid in our lab, but in industrial settings you do some places. Some people work with this substances all the time, and they need to understand and follow safety procedures. So very important. Here are some more compounds. Again, you're going to always see, if you're looking at the symbolic representation, which we call a formula, you're going to see more than one capital letter. If you see more than one capital letter, you have a compound. You're looking at a compound. Copper sulfate's one of my favorite chemicals just because it's such a pretty blue. We do use it in labs sometimes. Epsom salts, if you've ever had that at your house, you can buy that at Walgreens. It's magnesium sulfate. There's its chemical formula. It's a compound. So again, we can talk about the macroscopic properties of substances, the color, the texture, crystal shape, okay? And then we can talk about whether things are solid, liquid, and gas. But chemists also like to talk about what are those representative particles, which means, is this substance, does it exist as atoms or does it exist as molecules? And so when we do draw particle models, we draw, like I said, we draw a circle, and that represents an atom, okay? And here are some different kinds of molecules that we could see. And a picture like this with these 4 particles, there are a lot of different questions that could be asked about these. So look at these and try to decide, what do you think? Of the molecules, are they all compounds? Are they all elements? Or are some of those compounds and some of those elements? When we include the molecules and the atom together, how many of these 4 substances are elements? How many of these 4 substances are compounds? So if you decided that the atom is an element, you're absolutely right, that's an element. And then the molecule where the 2 atoms are identical bonded together, that's a diatomic element. So our bottom substances are our 2 elements. And then here we have our compounds, because we have 2 different kinds of atoms bonded together into a molecule. So we have 2 compounds and 2 elements, okay? The top 2, where we're looking at molecules of compounds. The bottom left is a diatomic element. The bottom right is a regular element. It's not diatomic. Particle models are really important. We're going to be using those a lot. So again, how do we distinguish elements and compounds? Well, on the left, we have a particle model, and it shows iron and sulfur. Those are elements. They're mixed together. So this, on the left, is a mixture of 2 elements. Notice they're not bonded together. It's a mixture of 2 elements. On the right, that's a compound. So we really are kind of looking at a chemical reaction before and after. Before, we had 2 elements that were in a mixture. They were separate. They were both present there. And then a chemical reaction occurred, and now we have a new substance, this iron sulfide, and we have molecules of that new substance. The sulfur's not there anymore. The iron's not there anymore because these are bonded together, and when we have a bond that happens, we get a new substance with new properties. Iron sulfate. Elements versus compounds. Okay, look at these. Let's talk about what we see in each of these particle models. We have substance A, substance B, and substance C. Which of these boxes represents pure substances, and which of them represent a mixture? Can you tell? Well, letter A is a mixture. You see, we've got the mixture of the blue molecules and the red molecules. We have two different substances there. That's a mixture. Substance B is a pure substance because all of the atoms present are the same in all of the molecules that are present. Okay, so all of the atoms or all of the molecules that are there are the same as the others. Okay, so for B, is it an atom or a molecule that you see? You can ask a lot of questions about this picture. Does this substance in substance B, does it exist as atoms or molecules? I hope you're choosing molecules because that's what it exists as. In the mixture, is the mixture made of atoms or molecules? There's two different substances, but both of those substances are molecules. Sorry. All right. Let's look at C. Is letter C a pure substance or a mixture? So we have one mixture in letter A. We know letter B is a pure substance. What about C? Is that a pure substance or a mixture? I hope you picked pure substance. I have room to get my E in there. I hope you picked pure substance. You see, all of the particles in there are exactly like all the others. So there's really only one type of matter there, and it's this piece. All the other pieces are identical to it. It's a pure substance. Okay. So is this substance made of atoms or molecules? Which one? I hope you're picking molecules, because when atoms are touching and they're drawn touching, that's a molecule. Okay. So we have a mixture, and we have two pure substances. Let's ask one more question here. These are great pictures to see on quizzes, hint, hint, because there's a lot of questions you can ask about them. So we've got a mixture, and we've got a pure substance, and we've got a pure substance. For letter A, is that a mixture of two, oh, wait a second. Is that a mixture of two elements? Is it a mixture of two compounds? Or do you believe that there are both elements and compounds present there? Think about that. For letter A, is that a mixture of two elements, or is that a mixture of two compounds? This is tough because this is all new to you. I hope you picked two elements, because what that is there's a diatomic element, a blue one, and a diatomic element, that's the red one. That is two diatomic elements mixed together. In letter B, it's a pure substance. So if we look back at our original chart, we said that a pure substance can either be an element or a compound, and that's all. That's the options. So with letter B, is that an element or a compound? Is that an element or is that a compound? Well, I hope you picked element, recognizing that we just said that this was a diatomic element over here. So this is that element, a pure element. Okay. Well, let's look at C. Is this, it's a pure substance, we already talked about that. Is this an element or is this a compound? I hope you picked compound, because you see we have two different atoms bonded together in a molecule of a compound. Two different. This screen is rich with question possibilities. So much so that I want you to see it again and think about what we just talked about. So, all substances are either pure substances or they're mixtures, okay? And we've been talking about pure substances, and now we're going to talk more detail about mixtures. And a mixture, the word mixture, that's easy. It's mixed, two or more things mixed, okay? And we talked already about how mixing of substances together is not a chemical change, it's a physical change, because all of those substances are still there and they retain their own properties. Just like we talked about in class, a trail mix. The raisins look like raisins, the M&Ms look like M&Ms, the peanuts look like peanuts. Okay, we can tell what's what. They're all those separate substances that we mix together are still there and they still retain their own properties. So it's a physical change making a mixture. Okay. Once we have mixtures, we can categorize them all into exactly two kinds of mixtures: homogeneous and heterogeneous. Homogeneous and heterogeneous. The prefix homo means same. And so when we're looking at a homogeneous mixture, we find out that the composition of it is the same all the way throughout. It's blended in such a way that both or many, there could be lots of substances there, but we'll just say there's two. The two substances are blended so that they're equally distributed together and all of the composition of it is the same. Now, trail mix isn't like that. You can find your raisins, separate them from the peanuts, right? Separate them from the M&Ms in a trail mix. But if you took that trail mix and you put it in a blender for a while, I'm not sure why we'd want to do that, but what if we did? Okay. Then we would have something that's homogeneous. It's all the same. We wouldn't be able to see where the pieces of raisin were anymore. where the pieces of peanut were anymore. Okay, so heterogeneous, prefix hetero means different. Our trail mix would be a heterogeneous mixture. The composition is not the same throughout. You can find the peanuts versus the raisins versus the other parts of your trail mix. Same, different. A homogeneous mixture has what we call a uniform composition. It means it's all the same. When people wear uniforms, they're all dressed the same, right? If it has a uniform composition, then it's all going to look the same. See that word a lot when you talk about homogeneous mixtures. Okay. So here's our chart we started with. All matter is all the stuff that we're investigating and exploring in this world. And all matter is one of two things. Either it's a pure substance. This is a good place to ask a question. What are the two types of pure substances? Because there's only two. Can you remember what they were? Because we just talked about them. Elements and compounds. So if it's not a pure substance, then it's a mixture of two or more. You can have a mixture of one. Okay? A mixture of two or more substances. And all mixtures are either homogeneous or heterogeneous. And see, there's that word uniform. Non-uniform. Homo means same. Hetero means different. We are learning a lot of words right now. I hope you like words. I like words. So here are some examples of homogeneous mixtures. Swimming pool water. You want swimming pool water to be homogeneous. You don't want things floating around in there, right? You don't want algae growing and floating through there, or leaves or dirt. You want it to be homogeneous water mixture. A steel spoon. Stainless steel is a homogeneous mixture of different metals. We can't see where the different metals are in there. They're blended uniformly. Air is a homogeneous mixture. It has a lot of nitrogen, some oxygen, some carbon dioxide, other things. But when we breathe it or look at it, we don't know where the oxygen is and where the carbon dioxide is. It's completely uniform. Okay, completely uniform. Salt water is a homogeneous mixture, and it is an example of one of our vocabulary words. It's a solution. What is a solution? It's a homogeneous mixture, by definition, in which one part, which we call the solvent, dissolves another. It's called the solute. So with salt water, the solvent dissolves the solute. With salt water, water is the solvent, and salt, sodium chloride, is the solute. And it's all blended in uniformly. Solutions are always such that the solute is completely dissolved in the solvent. Okay, so we don't see anything. You know, a precipitate, remember we saw the precipitates form? We took two solutions, and in a chemical reaction between those two solutions, which were both clear, we saw the cloud of a precipitate forming. Okay, both of those starting substances were solutions. So even though we don't see the particles, if we start investigating what's going on in the submicroscopic view, is those substances are all there. Okay, in this drawing, the little water molecules are the red and blue ones. And what's kind of interesting to note is water is smaller as a molecule size than many of the things that it dissolves. Okay, the water molecules are kind of small compared to these chlorine atoms that are dissolved in there. Okay. And water is what we call a polar solvent, and polar just is a whole lesson for another day, but water molecules have an interesting little thing that they do. They've got your oxygen side and your hydrogens, and they act a little bit like magnets. They have a little bit of a positive and a negative thing going on. You know how two magnets stick together because they both have a positive and a negative and the opposites attract? Well, that's how water works too. So water dissolves things because of the fact that it has that little magnetic property, and we will certainly talk about that in more detail at another time. Okay, but here's a picture of a little chunk of salt, table salt, and these water molecules are attracted to it and pulling the little pieces away, and then they surround those little pieces, and that's how you end up with a solution, because the water completely surrounds all the little parts of the crystal of salt. And then another example of a solution would be sugar water. If we dissolve sugar in water, we're going to get a solution. And here's a neat particle model. You can see the sugar molecule's much bigger than a water molecule, and yet water molecules can hold on to each separate molecule of sugar and keep them separated in a glass of sugar water, and we have a solution. Okay. Common solutions. We use solutions for all kinds of things, all our cleaning solutions. If you've ever heard them called cleaning solutions, now you know why. They're solutions. They're one substance dissolved into another. And most everything that we use is what we call a water-based solution, because water is what we call the universal solvent. So most all of our solutions, not all, but most of our solutions have water as the solvent and something else dissolved in it, which is solute. Heterogeneous mixtures are mixtures that are not uniform. So even if you see a picture of a beautiful beach with white sand, and from a distance all that sand looks the same, when you get up close and you pick up some sand in your hand, you will see that they are not, all those pieces are not the same. And so sand is an excellent example of a heterogeneous mixture. It's different. There's different pieces. Some of those pieces come from little bits of shell. Some of them come from a little bit of what we call sandstone. Heterogeneous. When we mix oil and water, they don't mix. And so when oil and water gets mixed, even if you try to shake it and mix it together, it layers out into separate layers, and that is a heterogeneous mixture. Oil and water. Dirt is a heterogeneous mixture. It also is, again, it looks kind of similar from a distance, but when you start looking into dirt, you'll see that there are different things. Okay? So here's a picture of what happens if you take sand and stir it into water. And you're going to see that the sand will settle out. Some of it's going to float around in that water for a while. Okay? It's heterogeneous. It's going to separate two different things. It's a mixture. Picture here of the sand in the water is a good example of a suspension. Some of the pieces of sand are in the liquid, kind of stuck up in the liquid. And if you've ever been to a suspension or been suspended, you're stuck somewhere for a day, aren't you? And so that's kind of what the word suspension means. Those particles are suspended in the water, but some of it is settling right out to the bottom, and that's a good example of a suspension. Here are some other heterogeneous mixtures. A lot of the things we eat, pizza, sandwiches, vegetable soup, a lot of those things are heterogeneous mixtures. There are two specific heterogeneous mixtures that are also on our vocabulary list, and one of them is called a suspension, and one of them is a colloid. Now, so a suspension is a mixture that is heterogeneous, and some of the particles will settle. And if you wait long enough, a lot of times most of them will settle. Okay. Italian salad dressing is a textbook example, and all the chemistry textbooks mention it. Any substance that has directions that say shake well before using is a suspension, like Pepto-Bismol, spray paints, you need to shake those. Okay. Any of those products that you need to shake before you use it. Chocolate milk, yep, lots of things. A colloid is a very interesting heterogeneous mixture, and we're not going to talk a lot about it right now, but you could spend days just talking about colloids. Colloids look like they're uniform. When you first investigate a colloid, you will think it's homogeneous, but it is not. Okay. Examples of colloids include milk and blood. Those are the two main ones you see on quizzes. Milk and blood. Okay. Ketchup is a colloid. Butter is a colloid. Mayonnaise is a colloid. Most of your dairy products since milk is a colloid, your other dairy products tend to be colloids as well. Okay. They do look like they're homogeneous, but if you investigate them, they are not. Okay. So here, these two words, suspension, there's my N that got misplaced in my program here. I don't like that. A suspension, a basic example of suspension would be orange juice, because the pulp tends to settle out. Okay, it's heterogeneous. And then again, colloids, they're really unique. Okay, they look heterogeneous, but when you investigate them, they really aren't. And one way to actually do that investigation is something that's called the Tyndall effect. And if you have a true solution like Windex or salt water, and all of the solute is 100% dissolved in the solvent, notice I'm using vocabulary words, okay? If all the salt is dissolved in the water, then if you shined a flashlight through that solution, the light would go right through without hitting anything because everything was dissolved. But if you're looking at either a suspension or colloid, because there's actually little particles in the colloid that are not settling out, okay? In a suspension, you have larger particles that do settle out. In a colloid, you have larger particles that are evenly distributed, but they don't settle out. And so with milk, we think of milk as being a liquid, and that's true, but the truth is, milk is a liquid with little pieces of solid all the way through it. That's why we can't see through milk. And if you take milk and add some water to it so that you can get those solid particles, which are basically the fatty parts of milk, to separate away from each other, then you can shine a flashlight through a colloid and it will it'll show up. Like if you've ever seen cars driving through a foggy day, fog is a colloid, okay? And those headlights show up because the light is bouncing off of those little particles. So with the Tyndall effect, anything that's a colloid, if you shine a light through it, that beam of light is going to show up in there because it's hitting all those little particles that are solid that are in that mixture. Okay. Lots of things are, like I said, butter, fog is a good example of a colloid. And then here's a real picture of a Tyndall effect. They're shining a light through these two mixtures, And in the solution, you don't see that light beam at all. But then on the right here in the colloid, you see there's nothing settling out there. And if you put your finger so that you're blocking that light, you would think that you had a homogeneous mixture there, but all those little solid pieces are reflecting light, and so the beam shows up in there, and that's just called the Tyndall effect. It's one way to check to see if everything is dissolved or not. Technically, that's what you're looking at. So again, what are we doing? We're categorizing all of matter. All of it can either be a pure substance or a mixture. Okay? And when we talk about pure substances, all pure substances are either elements or compounds, and all mixtures are either homogeneous or heterogeneous. This is a great chart to have. It's on page 28 of the PDF resource material I've left for you online, okay, in Schoology. And homogeneous mixtures include solutions, and heterogeneous mixtures include suspensions and colloids. My S got lost at the corner there. Okay. So other things we can talk about when we talk about different kinds of matter is we can talk about whether substances are metals or nonmetals. You're pretty familiar with metals and nonmetals. You've been around those to intuitively know most of the time whether you're looking at a metal or a nonmetal. But all of the elements are actually divided. Most of our elements are metals. And when you get your periodic table, you're going to find there's a little stair-step line that's slightly thicker, and that divides the metals from the nonmetals. And those elements that are on that line are called metalloids because they kind of have some properties similar to both. You can pause this and read this about how metals bond. That's not our lesson for today, but it's good stuff. Okay, but metals have properties. They have a luster. They conduct electricity. Okay, nonmetals tend to be what we use as insulators. They don't conduct electricity. And we'll talk more about metals and nonmetals later and their properties. Alloys, and I mentioned that because one of our words is an alloy. An alloy is a homogeneous mixture of metals. These metals mix together homogeneously, so uniform. And 3 common alloys is brass, bronze, and pewter. Others are stainless steel, chrome. When we talk about chrome wheels, chrome is a alloy. Here's our chart again. Organization of matter. Here's a different chart. I like it because it reminds us some important things. Same stuff is happening. Matter. Matter can be solid, liquid, or gas. And of course, the fourth state of matter that we never really talk about in our class is plasma. Matter can be divided into 2 substances, pure substances and mixtures. What I like about this one is this little addition. It reminds us that if we make a mixture, it's not a chemical change. It's just a physical change. We can make a mixture. It's a physical change. And if we want to separate a mixture back into the pure substances that are there mixed together, then it's a physical change to separate that. But if we're talking about the difference between elements and compounds, when elements become a compound, it's not a mixture. It's a chemical change. Elements combine to form compounds in a chemical reaction, and if you want to separate a compound back into its elements, it is a chemical reaction. So I like this chart because it reminds us of those important things. Here's another nice chart I found because it gives good examples. A pure substance mixture, elements, compounds, homogeneous and heterogeneous, with a lot of good examples for you to look at. And that is the end of this. It's a lot of vocab. We're going to be working together in class and using these vocabulary words correctly and talking in more depth about particle models. That's what's coming.